All right, so now it's time, since we've talked about bonding quite a bit in the last chapter, to move on to talk about molecules and their spectroscopy. So we're looking at electronic spectroscopy of molecules. And we start this discussion with the beginning of molecular term symbols. So they're similar to atomic term symbols. Instead of letters that we're used to in our alphabet, Latin letters, we're going to use Greek letters, but the order of the letters follows the same order. Instead of S, we have sigma. Instead of P, we have pi. Instead of D, so we have S, P, D, F, phi. And then gamma is G, and so on and so on. And we won't really see much beyond delta in most molecular cases. So we don't have to go ahead and figure out what all the rest of the Greek letters are the way we did for atoms. Spin multiplicity is computed the same way it was for atoms. Basically, any pairs of electrons add up to zero. Any unpaired electrons spin up is going to be plus 1/2, spin down is going to be minus 1/2. That'll get you S, and then the multiplicity is 2S plus 1. The lambda instead of L is computed similarly to the way it was for atoms. Any sigma orbitals have m sub L 0 for all electrons. Any pi orbitals have m sub L plus or minus 1. And so we'll look at some examples on this in a moment. Subscript G or U denotes the overall electronic symmetry for homodiatomics. Those subscripts won't be meaningful for heterodiatomics. And so, as I mentioned, we'll go ahead and look at an example for this. Here's the electron configuration for the oxygen molecule. Just like for atoms, only unfilled subshells are going to contribute to the overall situation here. So we're only really looking at these. We have 2 spin up electrons, and so we're dealing with a S equals 2 situation. I'm sorry, we're dealing with an S equals 1 situation, and 2 times 1 plus 1 is 3. So this is a triplet state, and this is going to be a plus 1 m sub L. This is going to be a minus 1 m sub L. So the total lambda is going to be 0. This is going to be a sigma molecule. Now, on this next slide, we've got listed a bunch of the other possible electron configurations for oxygen. In fact, the one that we just showed is the one on the third line here. It's a sigma state triplet. If both of those upper electrons were spin down instead of spin up, it would still be a triplet state because we use absolute value of S in that calculation, and it would still be a sigma state. But if we pair those electrons up in one orbital or the other, then we end up with a delta state because we would have 2 in the plus 1 or 2 in the minus 1. And because they'd be paired up, we would have a singlet state. And so there's all kinds of ways that those electrons in that upper sublevel could be arranged. And the only one that would reflect the ground state would be this one that we described on the previous slide. I want to point out the plus or minus superscript here. That has to do with how the symmetry of the wave function is affected by reflection through a mirror plane. We're not going to go to the trouble of learning how to assign those. We will talk about selection rules in reference to those. So I'll mention them, but I won't ask you to look at an orbital and tell me whether it's plus or minus. And so here's a few examples of some molecular term symbols for homodiatomics, both molecules and ions. And again, I'm not asking you to assign plus or minus. We'll talk about how it's useful to know what that is later on, but it's a little beyond the scope of this course to talk about assigning them. Um, and so let's take a look. We have in the H2 molecule, we would have 2 electrons in just the Garada. And so we'd have a Garada situation, singlet sigma state. Oxygen, we already talked about why it's a pi state. And so those are just there for examples. All right, now let's take a look at how we might use some of this. What we're showing here are the 5 lowest energy electronic states for the oxygen molecule. So we have the ground state here in orange. We have a first excited state here in green, second excited state in blue. And they each have a particular label, and we're going to discuss what those labels means in a moment. One thing I'd like to notice is that we're looking at the electronic energy and the vibrational energy. So that's why we have this Morse potential looking shape here. So a molecule could exist in this ground electronic state, but this vibrational state. Or it could exist in this excited electronic state and this vibrational state. And so each of these is describing a multitude of vibrational electronic states. The other thing to point out is that the 4 lowest, the ground state and the first 3 excited states, all break to the same pair of atoms. They all break to triplet oxygen, which is how we expect oxygen to exist as an atom. And so they all have the same products when we break the molecule, so those products have the same energy. So these are all asymptotic to the same line. But the 4th excited state, when it breaks, because of how we move the electrons around to get to this excited state, when it breaks, one of the oxygen atoms that breaks off is in a singlet state. All the electrons are paired. Think of it this way. We'd have 2 electrons in the 2s, 2 electrons in the 2px, 2 electrons in the 2py, and the 2pz might be empty. And so that's a less stable atom, so it's higher energy. It's also important because this is the reaction that UV light from the sun causes in the upper atmosphere. And so when UV light of the energy difference between here and somewhere above here hits oxygen, the oxygen breaks in this way and generates this oxygen. And because it has all of its electrons paired up and a completely empty 2p orbital, it's in really good shape to act as a Lewis acid. And so when it runs into an oxygen molecule, which has lone pairs, it can slide right in there and make the ozone molecule really well, which itself absorbs UV light and protects us even further from some of the more harmful rays that come from the sun. So that's a really important interaction. All right, now to get into this nomenclature, X is the word that or the letter that we'll use to symbolize the ground state for a particular molecule, a ground electronic state. And then any excited states that have the same spin as the ground state we'll give capital letters to. So this is excited state A because it's a triplet just like the ground. This is excited state B because it's a triplet just like the ground. And any excited states that have a different spin state we'll give lowercase letters to. So this is excited state lowercase a. It's a singlet B. And so that gets us into a discussion as to which states are going to be allowed, not necessarily the allowed state, but the transition, because one of our main selection rules is that we cannot go from no absorption of light will cause change of spin of an electron. So a transition from triplet to singlet state is going to be forbidden. So we won't see this transition. We won't see this transition. And it's important to us that those transitions don't happen because those are visible light energies. The difference between this ground state and this second state is visible light. And so if oxygen underwent those transitions, it would be opaque. We wouldn't be able to see each other through it. The transition from the ground state to excited state A is also forbidden. And we'll go through the rest of the selection rules to talk about why that's the case. For diatomics with smallish atoms, the change in letter, the change in lambda, can be 0 or plus or minus 1. So we're not violated in going from X to capital A. And then but sign change is forbidden. So if your ground state is a minus on its symmetry, the only excited states it's going to be able to access in an allowed way are going to be minuses. So the lowest energy electronic transition that happens normally, that is not forbidden for oxygen, is to go from X to capital B. Right? And that's the one I told you that goes on based on light that is, if we've got light that's less than 242 nanometers, greater energy than 242 nanometer UV light, then when it hits oxygen, it breaks it, and it breaks it into this much more unstable atom that likes to join up with other molecules to become ozone. And so next thing we want to talk about is the fact that accessing higher vibrational states is allowed. So if we're at the ground state and a photon hits this particular molecule that is of the energy to increase its energy to this state, the fourth vibrational state in this excited electronic state, it can absorb that and jump to that vibrational state. And in this particular case, it would be easier to absorb that light and come to here than to come to this state, because there is overlap between the ground vibrational state here and this higher excited vibrational state. Just based on the geometry of the molecule, we can tell that during this vibration, the geometry of this molecule overlaps with this. And that comes out in the math in what we call this overlap integral. And so being able to draw that straight line and get into, from the ground state or from whatever state we're leaving to the next state, and get into the vibrational pattern there, is referred to as the Frank-Condon principle. And so that gives us a way of seeing vibrational states even for nitrogen and oxygen that we can't do IR on, but we can see them jump to this level, and we can see them jump to other vibrational levels. And if we look at the difference between those energy levels, we can calculate vibrational levels. For example, like we see here. So we have, this would just be a UV vis peak for an atom. This would be for a diatomic. And the difference in energy between these peaks, this is one single electronic transition, but to several different vibrational states. And we can see the vibrational states just by subtracting those peaks from each other. Now, for a polyatomic molecule, the peaks won't resolve because we have so many different vibrations that can go on. Everything starts to overlap and we can't see things. But it would become easier to see those things if we can find how well the molecule can vibrate and rotate independently in a bunch of different modes at the same time. And so if we want to be able to see specific lines in polyatomic molecule spectra, like for methanol in this case, we could cool it down. So at 9 Kelvin, we see some much more resolved peaks than we do, for example, at 300 Kelvin in the case of methanol. All right, so just finishing up with this topic, we've got a few more vocabulary terms to look at. A chromophore is kind of like a spectroscopist's way of saying functional group. It's a part of molecules that absorb radiation nearly the same way in various molecules. So for example, you always see that carbonyl peak in the IR when you're in your organic class or instrumentation class. Carbonyl is a particular chromophore. Beer's law we're familiar with, a log of intensity later over original intensity of light that shine through a sample gives us basically absorbance. So absorbance is epsilon times path length times concentration. Epsilon is the molar extinction coefficient, and the molar absorption coefficient is related to the integral of that. So there's some vocabulary terms that might help with your reading if you're reading through the textbook on these topics. And let's talk about some specific chromophores. The N double bond O chromophore is undergoing a transition from an N orbital. We haven't talked about N orbitals yet, to a pi star at a lambda of 660 with a particular molar absorptivity coefficient. That N orbital is talking about, rather than a pi to pi star or a sigma to sigma star transition, that is talking about a transition going from a lone pair, a non-bonding pair, to, in this case, an anti-pi bond, pi star. And so there's several other examples here of various chromophores. When we see the benzene information, benzene rings are going to do something similar to this regardless of their environment. So if we're talking about toluene or paradichlorobenzene or something like that, it's going to have similar UV interactions to what benzene does. Carbonyl right here around 280, around a 20 for the molar absorptivity coefficient. We're going to see that on various organic molecules that have carbonyls. All right, so for example, here's a carbonyl compound, formaldehyde. We only show one sp2 orbital coming from the carbon because we're ignoring the CH2 part, right? So the other sp2 orbitals are going out to deal with the hydrogens. But one of those sp2 orbitals forms with one of the p orbitals on the oxygen a bonding sigma and an anti-bonding sigma. And then the unhybridized p orbital forms with one of the p orbitals on oxygen a pi bonding and a pi anti-bonding orbital. And then one of the p orbitals on the oxygen, the one that has the electron pair in it, when we think about oxygen's electron configuration of being 2s2, 2p4, so that would be 2px2, 2py1, 2pz1. That 2px orbital just becomes a non-bonding pair. The other non-bonding pair, if we want to think about two lone pairs on the oxygen, would be the 2s orbital. And so we've got that non-bonding pair, and we could symbolize another non-bonding pair with a 2s orbital. But what's going on is if we hit this oxygen, we hit this molecule, we hit this chromophore with just the right wavelength of light, we'll excite from that non-bonding orbital to a pi anti-bonding orbital, weaken the bond, and we'll have a situation of going from here, this electron configuration, to this one, or to this one. The triplet state is lower in energy, but it's a forbidden transition, so we won't see this happen, at least not normally, at least not very much. This is much more likely. Same thing if we excite an electron from the bonding orbital to an anti-bonding orbital, bonding to anti-bonding. We'll see these kinds of changes. And again, exciting from singlet to triplet is forbidden. It won't normally happen. And so this kind of diagram that we're showing here is referred to as a Jablonski diagram. And so what it tries to do is symbolize a ground state for a molecule and at least a couple of excited states that might be accessible. And accessible means something a little bit different than forbidden and allowed. So for example, if this ground state, when I say ground state, I'm saying ground electronic and ground vibrational. If that absorbs a photon that's enough energy to bring this molecule all the way to this singlet excited state, which is allowed because we're not changing spin, and this vibrational excited state up here, then we'll see that absorbance in our spectroscopy. And the question is, what might we see as an emission spectroscopy? Well, any wavy lines that are drawn on a Jablonski diagram symbolize transitions that happen without giving off a photon. So when we have this relaxation from a high vibrational state to a lower vibrational state, and we show it with a wavy line, we're talking about vibrational relaxation, or some people might call it thermal relaxation. That vibrational state is dropping without giving off any light, just through bouncing off of things. It's basically cooling down to this state. No photons given off. Once it's here, it's got a few choices as to what it can do. If it drops back to the ground state, we see a straight line, not wavy, so it's going to give off some light. That would be fluorescence. But it can jump from singlet to triplet, all right, so that usually unallowed transition, it can do that if the triplet molecule has roughly the same shape as the singlet version, and if it can make that jump without changing energy. So it can jump from singlet state relaxed vibration, singlet state, singlet excited state, but ground vibration, to the triplet state excited vibration. And then it can vibrational relaxation, thermal relaxation down to here. And then the interesting thing is there it's stuck. There's no allowed transition to get back to the ground state. It can either get back to ground state by what's called internal conversion. It's very similar to this intersystem crossing. Intersystem crossing is this non-radiative transition, non-energy change, where we're changing state. Internal conversion is where we're not changing spin state. And then it can vibrationally relax back down here. And so it can get back to the ground state without emitting any photons, all thermal. Or it can do this forbidden transition. And this forbidden transition is very, very interesting because it happens. And it happens and we can measure it. And the time is very slow. So if you had a toy as a child that glowed in the dark, it absorbed a bunch of light from the sun, a lamp, whatever you had. And then when you turn all the lights off, it glowed in the dark. What it was doing is phosphorescing. It was somehow the molecules in it absorbed that light, it excited them to a higher state, and through intersystem crossing, it ended up in a state in which it was forbidden to drop back down. It still dropped back down. It just did so slowly so that you could see it happening over time. And so we've got just a few more ways of drawing this out. Absorption is going to be either from ground, electronic ground vibration, to excited electronic ground vibration, or to some excited vibration. So it's always going to be greater than or equal to the least possible value. Fluorescence is going to be from ground vibration, excited electronic, possibly back to ground, or to ground with higher vibration. And so we see all of these purple transitions symbolized in energy here, where frequency or energy is on the x-axis. And so if we look at fluorescence versus absorption, they should have one peak that overlaps. And that peak is going to be the lowest energy transition for that molecule. What we've got here is another way of drawing out that phosphorescence situation. We've got, based on Frank Condon rules, a ground state molecule that can absorb to this singlet excited state with this high vibrational state. And as it relaxes back down, it gets to the point where it can intersystem cross to this triplet state. Once it's in the triplet state, it doesn't have a good way to get back to the ground except through phosphorescence. Phosphorescence frequencies are always going to be less than the absorption frequencies. Right. And that's pretty much main things that I wanted to talk about in this section.